I'm going to talk today about why I think simulation's a frontier problem in data science, and that's just in its early stages. I guess I'm somewhat motivated at the beginning, the Alan Turing Institute had a narrower focus on machine learning, and so I may be preaching to the choir at this point, but I'm urging for that to be broadened. I was influenced to do what I'm doing now by the experience I had from 1991 to 1999, starting something called Prediction Company. We were one of the earliest purely quantitative trading funds. We were also a purely automated trading fund. By 1995, we were trading in markets without any human intervention. It was founded by Norman Packard and myself. We were at least the senior founders. There were some junior ones too. I left in 1999. It was sold to UBS in 2006. And then because of the Volcker rule, which said that banks can't do proprietary trading, commercial banks can't do proprietary trading, it got resold to Millennium. And it's still going. And they have an excellent trading record at this point. The basic thing we did was to use machine learning methods to find reproducible patterns in financial time series. So we would observe that a certain set of things happened, and that historically when those things happened, that meant that a price on something went up or down, and we would make a bet on that. We didn't understand what was driving those movements. It was just a stimulus response box, and so I thought of it as a financial cerebellum. And here I'm being rather loose in thinking about the functions of the parts of the brain, but you know, the cerebellum's involved in coordinating motor activities. And whereas the cerebrum, again, in some metaphorical sense, is where you think about stuff, where you say, well, I'm going to do this because, and you have a set of reasons. So I got very curious to go back and do what we've done there, but actually do the because part. And I combined my background in complex systems with my domain knowledge in finance, and that's what I've been working on ever since. Let me also just make another background comment. As I look back during my career, what's been the biggest factor driving scientific progress across the board? I would say it's been the ability to simulate stuff. I was, to motivate that when I was a graduate student, so this would have been in the 70s at UC Santa Cruz, Stan Ulam came to give us a talk. Stan Ulam is one of the greatest mathematicians of the 20th century. And his talk was on nonlinear mathematics. And he began his talk by apologizing because he said to talk about nonlinear mathematics is like giving a talk about animals and characterizing it as a talk about non-elephant animals. Because, of course, most mathematics is nonlinear. Most things in the real world are nonlinear. And the reason that we've had so much focus on linear methods is because that's what we could do. We were the mathematicians under the lamppost searching for our keys there, even though we knew we had lost them somewhere else, because that was all we could do until the computer came along. Stan Ulam, by the way, was one of the early pioneers. He wrote a much unrecognized paper on chaotic dynamics simulating nonlinear maps in 1952. So one of the early research uses of the digital computer. Now, social science and economics in particular hasn't benefited from the ability to simulate things on a computer the way physical sciences have. And so, so that's part of what motivated me to work on what I'm working on now, because one of my rules of thumb in science is look for the things that haven't been done, find the low-hanging fruit and go there, because there are lots of people out there that are smarter than I am. Maybe you have a little better judgment about what to work on. You can do a bit better. Now, I'm a physicist by training, but I want to make the obligatory statement that social science isn't physics. I recognize that. People can think, atoms don't think. It's a much harder problem to make social simulations. And it's really easy to get lost. But nonetheless, I think there's a lot of things that can be done. And while people might be complicated, they do follow rules. Psychological experiments are highly reproducible. And we have big data now. The internet is capturing things about what people do at a rate that's far beyond anything that was being done before. Now, One of the other things computers have given us is big data. We can store lots of data in computers. We can process lots of data in computers. And that's super important, too. Machine learning is a field where we see the outcome of that now. I've tracked this through my career. When I was at Los Alamos, I was the first leader I started the complex systems group at Los Alamos in 1988. And I had people in my group doing machine learning. Some of the things I did were machine learning. And so I've seen that field go from its early stages to present. And there was a breakthrough circa 2008 or 9 with deep learning and the ability to make machine learning models that were enough better than what had been before to really accomplish lots of problems that couldn't be solved earlier. That was partly due to, significantly I would say, due to bigger machines, also partly due to the machines allowing people to do things that would have been unfeasible back in the 80s when we were doing it at Los Alamos. Now, machine learning is great. I'm all for it. As I already said, during my time at Prediction Company from 91 to 99, we really pushed the state of the art in machine learning and doing stock market prediction. And so it's a great thing. But you should bear in mind that machine learning is just fitting nonlinear functions to lots of data. It's statistical analysis on steroids. And so there's some fundamental things it's just never going to do. In particular, if you're, say, trying to do a time series model, machine learning models are just as good as the data that you have to fit on. And if the world changes for some reason, and you don't have examples of past data that represents the world that you're trying to understand at present, then you're dead in the water. Simulation model, on the other hand, is based on a fundamental understanding of how things work. When you make a simulation, you take the world as you understand it. You try and program in all the causal mechanisms that you know are there. And you may still need to do a lot of calibration, but you've built in a lot of fundamental knowledge about the way things work. And in a sense, you're building in a much stronger prior. That potentially gives you a lot of power, because with a simulation model, you still have to have some sense in which the past is like the future. That problem hasn't gone away, but you're modeling it in a more deeper, hopefully a deeper and more abstract way, because say if you're doing social science simulation, you're modeling the way people think instead of the patterns of what the decisions they made actually imparted on the world. And so if you enter a new world, and if your model's good enough, then you should be able to carry the model over into that new world. Of course, it might not be, and you might discover that you just didn't do a good enough job. But in particular, the key thing that it allows you to do is policy analysis. So in a policy analysis situation, you want to take a policy which may not be something that that's ever been used before, and you want to understand what its effect on the world would be. So in a good simulation model, if you're capturing in a more fundamental way the way people make decisions, you may be able to do policy analysis and get reasonable answers. You can't do that with a machine learning model. Now, simulation in social science leads to what's usually called agent-based modeling. So agent-based models are a class of computational models for simulating the actions and interactions of autonomous agents. And the agents could be individuals, or they could be collective entities like institutions, but with a view to assessing the effects on their system as a whole and thinking about the emergent properties of the world that you're simulating. Now, traditional economic models, and I'm going to stress economics because that's the field I've been working on for the last 25 years or so. And if you go say, well, how do economists do this? Well, first of all, their models are, in a sense, they're also agent-based models. They involve agents who make decisions and who think about the world. In a typical model, you assume the agents have preferences and beliefs, and you find a fixed point equilibrium where the agents maximize their preferences according to their beliefs. And in the strong form, the preferences are utilities, and the beliefs are based on rationality, which means having an accurate statistical model of the world. And you know, economists know that there are problems with this approach. They've been working over the last 20 or 30 years to modify it by putting in constraints, often they're called frictions, and that capture the ways in which this sort of pure 1970s style rational expectations model isn't true, through things like asymmetric information, institutional constraints, making only some of the agents rational, and that's the program that's been followed. Now, I think one of the central problems with this program is that it's based essentially on closed form solutions. So that means you're sort of tying at least one hand behind your back, saying, well, we're going to require that people have closed form solutions. And, you know, I love closed form solutions. You know, I've derived many myself. They're elegant, they're great. But there's just a lot of problems where you just can't do that. And if you're trying to model the real world and say, I'm only going to do it through models with closed form solutions, you're really imposing a huge restriction on what you can do. Now, this is in part because in a model that's based on rationality, if you make things simple enough, you can compute what the rational agent would do. It's much harder to compute what a rational agent would do when you're dealing with a less specified, more complicated domain. You're typically dealing at best with partial or bounded rationality. Now, why then should we be doing agent-based modeling? For economics, it would diversify the toolkit. You know, one of the principles we know from finance is that if you have a positive you have a positive return on an asset, and if it's not perfectly correlated with the rest of your portfolio, you should put some weight on that asset. The way mainstream economics has worked is put extremely little weight on that approach to doing science. Increased computing power and big data, better behavioral knowledge mean that it gets easier and easier, and we're more and more ready to do this kind of thing. I would argue that in economics, at least, it hasn't been tried properly yet. I make these estimates of how much effort has been spent. The estimates are now getting a little old, but you know, maybe mainstream economic models have 30,000 person years behind them. Econometric models have 20,000 person years. Agent-based modeling in economics might have 500 person years. So vastly smaller amount of effort. There are successes elsewhere that are at least partial proof of principle in traffic, epidemiology, defense, maybe actually in spatial modeling and geography. And there are actually some successes in economics. I would argue that if you want to understand why financial markets have clustered volatility, that agent-based models provide really the only plausible explanation. And what do I mean by clustered volatility? Well, if you look at financial markets and you look at the returns on an asset, there are periods where returns don't fluctuate very much. There's very little volatility in the market. There's other periods where markets become very volatile. It's a highly intermittent time series with lots of structure. You can generate with agent-based models time series that look just like that. That's generated by the endogenous dynamics of the market itself. And you can refute the counterargument from the other school of thought, which is that, well, volatility is just a reflection of information, the rate at which information is flowing into the market. If I had more time, I could go through that and show you that that just can't be right. The majority of what happens in financial markets has to come from endogenous movements in the markets, and agent-based models are the only explanation. Actually, there's two explanations. One is based on a kind of ecological explanation of trend followers and value investors. The other one that actually I'm responsible for is leverage. It turns out leverage can give you just those kind of series. That is, as soon as people borrow money to buy assets and that they couldn't buy themselves, then you get this kind of behavior in financial markets. Now, there's a lot of advantages to doing an agent-based model. You can faithfully represent real institutions. You can easily capture instabilities and feedback. Nonlinearities, heterogeneity, network structure, all those things are relatively easy to do in an agent-based model. You can capture the endogenous dynamics of things. So you don't have to rely on a static equilibrium assumption where the dynamics is coming from shocks from the outside world. It's easy to do policy testing. You just put the policy in your model and see what it does. It's easy to incorporate behavioral knowledge if you have it. That is, you can make your agents follow some behavioral rules that say, a psychologist gives you. You know, because you're working at a microscopic scale, because in an agent-based model, you're typically simulating individual institutions at a more fine-grained way and then aggregating things up to look at the macro scale, you can potentially calibrate the model in a richer way. And I'll come back to say more about this in a minute. And you can use it to synthesize knowledge. You can take what you know about different things in the world, put it all together, and do a simulation and see whether it works. And if it doesn't, because it probably won't when you first do it, you then can start picking things apart to understand what is it that you really don't understand. Where are the bottlenecks to your knowledge about the world? And you can focus your effort on those bottlenecks. Now, I don't want to give the impression that this is a panacea or it's easy. Quite the opposite. There's a lot of challenges to doing this kind of thing. There's little prior art. It can be hard to develop the right abstractions. There's no sort of pre-packaged frameworks in which you can just operate. You always have to make decisions about what you should include and what you should omit, because if you try to simulate the world at the level of the individual atoms, well, you're stuck. Individual agents, you're probably still stuck. So you typically have to make abstractions about what properties do you care about, what do you put in the model, what do you leave out. And you have to still leave out most things in a good model. I've already mentioned microdata. I'll come back to say something about that. These models easily get complicated if you're not disciplined. In fact, they may get complicated even if you're not disciplined, because you really need the complication in there to model what you're modeling. And you need to have ways of coping with that. You need to avoid the black box problem. It's very common in agent-based models that you put a lot of stuff in your model, you push start, it does something, and you go, wow, why did it do that? And you have to be able to go in and diagnose what's driving what. And I could give you some examples of that. I'm not going to talk too much about the art of doing this today, but I'm going to talk more about the fundamental theoretical challenge for data science that puts this problem, in my opinion, squarely within the scope of the Turing Institute. I wrote down there a cautionary tale of weather forecasting. I'll come back and actually say more about that a bit later. Now, let me just say a little bit about my own design philosophy with these kind of models. You should first of all make them as simple as possible. Now, you may not be able to make it may not be possible to make a very simple model that captures what you want to do. But you really ought to focus on modeling the essential things and leaving out anything that you can possibly leave out. You should design models around data. I'm interested in quantitative models. You should really go look at the data you've got before you start building the model, so you know what you're going to be able to calibrate against, and so that you've really thought about what it is that you should be putting in the model and what you can do. I've already mentioned this several times, I guess, in this talk, which I should say this is a bespoke talk, so it's not a highly polished talk I've given 5 times, but I am grabbing slides from different sources, so there may be a little bit of repetition. There's a lot of ways you can calibrate models. You can go get microdata on what the agents actually do. Try and calibrate the model that way. You can consult domain experts to see what behavioral hypotheses should you put in there. You can put in some optimization in your model. If you want to model the reasoning powers of individual human beings, well, we may not be fully rational, but we're also not totally stupid. So you can put in things that try to find that sweet spot between totally stupid and perfectly rational. You can do economic experiments. Increasingly, people do experiments, and you can set up experiments that test the aspect of agent behavior that you want to understand and calibrate your model against the way the agents actually behaved in the experiment. You should always systematically explore model sensitivities. What does this model depend on? Because oftentimes you find that some of the parameters make a big difference to the outcomes. Other parameters are pretty irrelevant. You need to make these make models plug and play. Why? Because you always come back to the black box problem, and your model does something, you want to understand it, you need to be able to quickly simplify your model, test alternative hypotheses, and try and put your finger on what's actually causing what. Make standardized interfaces so you can couple different versions of the same basic task together, and of course, good software standards, and I'm a strong believer in open source. Now, I think I already covered this. Let's see if there's anything left out. Well, I should say that actually the most commonly used approach, in my opinion, is to just make stuff up. It's not a crazy thing to do when you're getting started. You make something up to understand the basic problem domain, but then you need to quickly go back and put in the right agent behaviors. And I also want to emphasize that in social science, the hard part is always modeling the decisions of the agents. You can usually make quite accurate models of infrastructure and of the mechanical aspects of the problem. That's where you really shine relative to the other more standard economic approaches based on the one I showed you. Where you can founder, if you're not careful, is in not having good ways of modeling the decision rules. So I want to give you an example now of housing markets. So this is a project that was funded on a shoestring. It was a ridiculously ambitious project funded on a shoestring. We didn't get the final polished model we set out for, but I think we did a lot of interesting stuff. And so we had 4 senior collaborators, Rob Axtell, John Giannakopoulos, Peter Howard, and myself, and then a set of junior collaborators, including Ernesto Carella, Ben Conley, John Goldstein, Matthew Henry, Philip Kallichman, and there were actually a few others by the end. The goal was to make conditional forecasts and do policy analysis. We simulated at the level of individual households, and we simulated specifically their decisions to buy houses. Should you rent or should you buy? And should you go on in the house you're in, or should you move? If you're going to sell your house, how should you go about doing it? What price should you ask for your house? How should you mark that price down as a function of time if the house doesn't sell? And so on. We took a lot of things as exogenous. We took the demographics as exogenous. We focused on Washington, D.C., I should say, because George Mason University, where Rob Axtell was based, was in Washington, D.C. We managed to get a lot of data that was specific to Washington, D.C. Like, for example, we had the real estate records from the MLA. So we had every time a house was put on the market, we knew what price it was put on the market for. If the price was marked down, we knew what it was marked down to and when. If it was sold, we knew the price it was sold at for all houses that were sold through real estate agents in Washington, D.C. So it wasn't every housing transaction, but it was 85 or 90% of them over a period of about 13 years. We had data from the census. We had data on every mortgage that was given out in Washington, D.C. during that period. So we couldn't link that up with the individual houses in the other record, but we did know what mortgages were given, what terms were the mortgages given on. Some data from the IRS, we actually knew how many people moved into Washington every year, how many people moved out, what was their age, what was their income bracket. So we had a lot of data. And by the way, I guess I didn't say as I was explaining it, what were we trying to do? We were trying to predict house prices, inventories, default probabilities, about 12 different properties of the housing market altogether. And just to give you a feeling for the way this model worked, we would model the individual household, and when they decide they wanted to sell their house, or buy a house, rather, we would had a model for what house price bracket were they likely to look in. and based on their income and wealth, which we could calibrate against data taken by the US Census. We had a seller's pricing model that made use of this real estate data I mentioned. We would look at, once they decided to sell, we would have a model for what price they would offer their house at, and then how they would mark it down through time. We would match up the buyers and sellers. We would look at household wealth dynamics. So we'd model the consumption and savings of the individual households. And very important for this model, we had a model of loan approval, because most people have to take out a loan when they buy their first house. It's a very important activity. And so we modeled what banks were doing, and because we could see what mortgages were given year by year, we could see how lending policy changed through time, specifically for Washington, D.C. And we were, just to see how the model worked, at each time step, we'd input the changes to the exogenous variables. We simulated on a time scale of a month. We'd update the state of the households. How did their income change? How did their consumption change? How did their wealth change? Are they going to foreclose on their mortgage or not? We would model the buyers. Who's going to be a buyer? What price range? Do they need to apply for a loan? If so, what kind of terms do they get, if any? Maybe their loan approval is rejected. And then we would look at the sellers, and then we would match the buyers and sellers, compute new prices and transactions, and move the model forward a month and repeat. So what could we do with the model? Well, this shows some results that we got. We would compare, say, the solid line here is the model. These are the dates over the period. This was the target data that we were trying to fit, which was the Case-Shiller index for Washington, D.C. So it was normalized to be 1 in the starting date of 1997. We would simulate the model across the period, and we would compare the Case-Shiller index generated by the model with the Case-Shiller index generated by the data. We could also look at things like the number of units sold or the days on market, and we had about 6 or 8 other characteristics like that we looked at. And then we could look at we could do counterfactual experiments. So for example, we could say, instead of this simulation, which was being driven by the changes in interest rates that were actually happening month by month through this time period, we could say, what if the Fed had just held interest rates constant? So we could simulate that world, and you could see we now get a different outcome. It has a significant effect on housing prices, but the bubble's still there, the crash is still there, but they're both muted. On the other hand, what if we just held lending policy constant? So when I got my first loan back in the olden days, the way it worked in the US at the time was you would put 20% down, they'd give you a 30-year fixed rate mortgage. That was just how it was done. And so, okay, they weren't all that, but back in 1997, that was still the prominent way it was done. We matched the way loans were being given out in 1997. We just held it constant through the period, and you can see that what happens is the bubble just flattens. So, in other words, we don't think there would have been a housing bubble, at least in Washington, D.C., if lending policy had been just held constant. So we do point our finger at that as the primary culprit. Now, let me make a few cautionary remarks. This is better than this looks better than it really is. This model is substantially overfit. Because how did we get this? We diddled the parameters to match the data. So really this is just a proof of principle. This is a proof of principle that we can match the data with a model that we built. And then these experiments should then be taken with a grain of salt, because I can't really guarantee how realistic that model is. And in fact, what we did was we went back with the individual modules. I showed you some of the individual modules, and we tried to calibrate each of those models, independent modules, independently of the target data that we were trying to fit, without looking at that target data. In other words, we didn't look at any of these time series up here. We looked at other time series. We fit those modules as well as we could. Then we tried to put everything together and run the model. When we did that, our results are much less good than this. Maybe I should have showed you what those kind of results look like. But you know, they were still not bad. And though we still were not fully happy with some aspects of the model, we ran out of funding, and I'm very embarrassed to say we never produced a proper paper on this. Now, the project kind of emerged from the ashes with a model that we made together with the Bank of England, where we used a lot of what we had learned in the Washington, D.C. model. We simplified a lot of aspects of the Washington, D.C. model. And we put together a model that we actually used to give advice to the Financial Policy Committee. They were contemplating a restriction on banking that that required that 85% of the loans that are given by banks have a loan-to-income ratio below a certain number, and 3.5. And so we simulated that, and we showed that actually it did seem to have a beneficial effect in damping housing bubbles in the model that we did, and they did implement that rule. Now, whether we had an effect on it or not, I don't know. And you know, and to be honest, I don't want to argue this model is not a detailed, well-calibrated model of the UK economy, though we did try to calibrate many aspects of it to it. It's a sort of proof of principle that this can be done and that this kind of thing can be useful. Now, I want to home in on some of the challenges, because I want to talk about the problems more than the solutions in this talk. There's a big challenge in agent-based models of estimating parameters. And you know, how are you going to make good estimates of parameters? Let's assume that you're doing it by matching data in some way. What's the best way to do that? There's also a big problem in initializing the model. In fact, in the Washington, D.C. model, to put the model in this initial state to match Washington in 1997 was a huge amount of work for us. Why? Because the model generates a bunch of endogenous dynamics. You know, you put the agents in some initial state, you push go, they start buying and selling houses, and even if you hold all of the background factors constant, it's going to take them a while to settle in to a steady state. In fact, in this model, it took us about 100 years of simulated time, which is already telling you something interesting about housing markets. There's long time scales there. But it meant that in order to get the model so that we were matching these macroscopic features like the Case-Shiller index or the number of units sold and so on in 1997, we had to do a rather time-consuming and tricky process of, you know, starting in 1897, running the model forward to 1997, and going, well, this is okay, that's not so okay. We go back to 1897, run it for 100 years, holding all of the inputs constant at where they were in 1997. I should have made that clear, till we landed at a reasonably close place to 1997, and then we ran it open loop. So this is an open loop simulation. We aren't updating this model as we go along. We're just recreating the bubble, you know, over a 15-year span from a single starting condition. Now, if you actually want to make forecasts, that's not what you want to have to do. You want to be able to run it forward for a year and go, well, we missed on this, we missed on that, readjust the model, run it again. That's how you do time series forecasting, which has been one of the things I've done, one of the main things I've done in my career. So just running this model and doing time series forecasting with a simulation model is challenging. And it's in part of the reason for this challenge is because this model is a dynamical system, and that the dynamical systems have attractors, and it takes about 80 to 100 years for this system to settle down on its attractor, where all the microstates of the model, we were simulating 10,000, or actually in some of these simulations we simulate 100,000 agents, and those agents have several pieces of information that characterize them. So you have the order of a 1,000,000-dimensional state space for this model, and you have to respect all the internal consistencies between the microstates of these agents, which simulating for 100 years does. But without doing that, you can't do it. If you just take those microstates and you just, grab them and modify them by hand to match the macrostates you want to match, you're probably going to do it in a stupid way. You're not going to respect these correlations, and you're going to end up with a horrible transient. And we tried this. We get a horrible transient when we tried to go forward and forecast, which is why we ended up running open loop. So validation's, of course, a problem. Attributing causality is a problem. But I want to focus, well, actually, maybe I should say a little bit about parameter estimation first. And then I'm going to focus on initialization, just because that's a problem I have a partial solution for. So first of all, usually ABMs don't have closed form expressions. So that means you can look up the literature on parameter estimation, and you've got to throw a whole lot of those techniques out the window because they require having a differentiable representation of your model. And it's not just that you don't have a closed form expression. You typically are generating some random numbers as you go along, and you have if statements. So that means there's discontinuities in the model behavior, and those discontinuities can cause you a big headache if you try and use standard parameter estimation techniques verbatim. These models are often complicated, which means there's a significant danger of overfitting them. Assuming I don't have to tell anybody what that means, but you fit to the data that you have very well, but you're not going to generalize when you go out of sample. And the typical thing people do is you pick a bunch of characteristics that you care about, and then you try and minimize the distance between the output of your model and those characteristics. The characteristics can be something like match this time series, okay? Or it can be match these moments of the world. And so, that's not too hard to do, although even there it can involve a lot of computer time. There's a lot of need for bringing in more sophisticated methods like Bayesian approaches and doing them in a situation where you don't have a closed form expression for your model, but your model may have some continuity even if it's not fully differentiable. Now, I want to talk about the problem of time series forecasting. As I've already mentioned, ABMs often have unobserved microstates. In our housing model, we weren't able to observe the individual households. Of course, that would have made it way easier. If we could have just had detailed data about each household in Washington, D.C., we could have gone to town. We can make a fantastic model that way, but we didn't have that. We still want to make forecasts of macrostates. The macrostates, though, are aggregated microstates, because how do we get the Case-Shiller index in the housing model? Well, we take the individual 100,000 households that we're simulating, and we take the prices of all the houses that are being sold, and we make a Case-Shiller index out of it, just like Case and Shiller do when they constructed the index for the economy. So we've got to alter those microstates, and then there's the danger that I said of sort of slamming the model into states that you didn't, in a graceless way that leaves you with a big initial transient because you've shoved the system off its attractor. Okay, so you need to be consistent with that attractor. And so this, I'm going to now talk about some work I've done with Juan Sabuco, who's sitting right here in the front row. We spent some time searching around for a model of appropriate simplicity / complexity. We need a model that has the problem of having unobserved microstates, but we wanted the simplest one we could get. The housing model's a little too complicated to build muscles on. And so this is a simple model where you have predators and prey. They live on a two-dimensional grid. The prey compete with each other to collect food and reproduce. The predators compete to hunt the prey and reproduce, and they both diffuse around the grid. And the goal now is to forecast the predator-prey dynamics in this model and to come up with a way of gracefully matching microstates. So just to give you a little bit of a feeling, here's a snapshot. This is work in progress, I should say. This is the first time we've talked about it in public. We don't have the paper written up yet. But So here you see a snapshot of the world, of at least part of the microstates of the world, where you can see at least where all the prey are and where the predators are. The prey are red dots, the predators are blue dots. We obviously need to make these bigger, but hopefully you can at least get the sense that they're scattered around there. And you'll notice that they're clumped. We didn't start it that way. We start out with them uniformly distributed, and they clump themselves. This is a common thing you see in ecological simulations, actually. And so you see clumps where there's lots of predators, empty space, other places where you have a higher density of prey. And this dynamically changes as you simulate, and apologies that I don't have the movie. Now, we want to align the microstates so that they reproduce macrostates. Our goal is specifically to match the population of predators and the population of prey at any given time, because these are fluctuating through time. And you'll see examples in a minute. It's well known in this kind of thing that you get endogenous fluctuations. So one thing you can easily convince yourself of is if you just let it run for a while and you want to make a prediction and you take the microstates and you just slam them into some new, you just add a bunch of animals, for example, because you discover that you don't have enough to match the observed time series, and you go forward, you just get a hopelessly bad forecast. So what we did here is what we're calling nudging, which is rather than altering the microstates all at once, we alter them incrementally. And we live with some deviation with the macrostates. We don't match the macrostates perfectly, but we still do better than we would with just doing everything suddenly. And in particular, there's a lot of questions you have to answer with in finding the optimal nudge. Which microstates should you alter? How should you alter them? How long should you nudge, and with what intensity? And I'll come back and explain that in a moment. So for the predator-prey system, one thing you can easily convince yourself of is that if you just add or subtract animals suddenly to fill up the deficit, and you just spread them randomly around the two-dimensional world, you get complete garbage. We found that if we tried to match the observed probability distribution by replicating existing individuals, so we take an existing individual, let's say we need to boost the population. We take an existing individual, we replicate an individual like that who we put near that individual, and we do that as many times as we need to match as much as we need to, then we get a much better result than if we just put them somewhere at random. Now, the nudge then works like this. We have the equation that we're running that determines the predators at time step in plus 1. It's some function f of the number of predators at time, and actually the geographic configuration of the predators at time n plus 1, and yn, the number of prey. And similarly, you have an equation for the prey. So this is what the dynamical system would be like if we weren't nudging. We intentionally alter the dynamical system to add terms that involve some constant that allows us to control the intensity or the size of the nudge. And we base the size of the nudge on the difference between the observed population and the population that exists in the simulation at that point in time. And then we can play with these constants. And we can turn the nudge on and off. And so maybe not surprising, if you make the coupling too strong, then the model just blows up. Here shows what's actually going on with the thing you want to match. This shows the nudged time series, and you can see that we're nudging too hard. We get these over oscillations, and it just blows up. If you don't nudge enough, you also never get it to match. The two things, you see similar behaviors, sort of, but they never line up. So you have a Goldilocks problem, turns out. You can do it, but you have, not too big, not too small. And so what's happening in this slide is here's time on the x-axis. Here's the number of predators, just for comparison on the y-axis. You see the two simulations going on with the simulation in red, the real system in blue. And by the way, here, we're just using, the two simulations actually have the same parameters. So we're not dealing with the fact that in general, you have different parameters in your model because you actually don't perfectly understand the real world, or your model just isn't representing the real world accurately. But now we start to nudge, and you can see after some nudging, things start to line up reasonably well. And then to see what's going on, we turn the nudge off again, and now you see the simulation start to diverge from the target time series again. And one way to think about this is we want to make a forecast at this place where we turn the nudge off, because of course you can't see that going forward. So we want to find something so that the simulated system will stay as close as possible to the real system after we stop the nudge. And so here you see an example of turning the nudge, again, turning it, it's off, it's on, and then it's off again. And with some set of parameters for this constant k that we found by searching to find the ones that seem to work the best. So you can see that if you zoom in, here's where we're nudging, so we're keeping things close together. We turn it off, things diverge. And now what we're going to do is take statistics on that to see how good is our forecast when we're doing this. So this is now blowing up the area shortly after the nudge stops happening. And you can see a comparison of 3 time series. One time series here is a time series for the error when you do a sharp nudge. So you suddenly say, okay, we're going to match the number of prey and the number of predators by throwing them in there, okay, using the best method we have, which is to replicate individuals. And so we get a perfect match at the beginning, but then you can see that decays really rapidly through time. We don't do a great job of forecasting. The black, in contrast, is the perfect situation where, okay, where we have the actual model and we observe the microstates, and we now have noise in this model, though, so the noise realizations are quite different. We repeat that lots of times and take an average in forecasting the error going forward with a perfect model. And how is the nudge doing? Well, it's in between those two. So this blue is the nudge solution. So we've clearly made an improvement over a sudden nudge. We're not meeting the theoretical limit of matching the microstates in detail. Now I'm going to zoom out in time. You can see when you zoom out in time a little bit more that we actually, our nudge solution is only better at short times. Actually, for longer times, it does worse than this sudden nudge. We have some ideas about that. We don't fully understand it. But it does say that, you know, it's limited in time scale for which it's useful. And now you can see a even longer time scale where you can see that asymptotically everything's converging as you expect it to do, because asymptotically all you can really do is make statistical predictions. And if you go far enough forward in time, all these are the same. Now, I want to make some more general remarks. You know, it's worth looking at other areas and asking how did they do it? So weather prediction is a good example, as I already mentioned. Prior to 1980, it's worth saying, how do we make weather predictions? They were done by subjective weather forecasters. And how did they go about their business? And they were doing this since the middle of the 19th century. There were published weather forecasts in newspapers by subjective weather forecasters. Well, after the invention of the telegraph, it became possible to assemble a weather map. And people began collecting books of these weather maps. And so you would get a pattern, you know, today's weather map. And these guys, I think they were mainly guys back then, and they had beards like me. And they would, you know, stroke their beard and, yeah, okay. That reminds me of 1935. Flip through, remember, no computers. So you go find 1935, find a weather pattern, find a few that made good matches, use intuition, put something together, look forward a page from the one that match to see how that storm unfolded, and find a few analogs. So they're using the method of analogs, and then they make a forecast, after doing that. Now, you might laugh, but it wasn't until 1980, and I was at the time an intern working with Ed Lorenz at the National Center for Atmospheric Research, and that was the point where numerical weather forecasts actually started to break even with subjective weather forecasts. And since then, there is a kind of Moore's law for weather forecasting since 1980, which is that every 10 years, the forecast at day n becomes as good as the forecast at day n-1 10 years earlier. So there's been enormous progress in weather forecasting accuracy. How did that happen? 3 reasons. Better models. I mean, there's been a lot of research about how to do weather forecasting. Bigger computers, which is huge, because it allows you to go to a finer grid and simulate things faster, and better data, particularly through satellites. And let me see, one of the key things that's been involved is data assimilation, what's called data assimilation. That is, you take the satellites, which actually don't observe the data in the form that the initial conditions that the model wants to take. The model wants temperature, pressure, wind velocity, et cetera, on a nice square grid. The satellites give you columns of stuff, where the same vertical column is put together on some moving set of grid points. But the weather guys have been very clever in figuring out ways of taking this data that's not the data they want and figuring out how to use it. This is going to be essential. And let me just give an example from a paper of my own. This is a 1980 paper. We wrote this when we were in graduate school. What we realized, our goal at the time was to understand chaotic attractors in physical data. We simulated them on analog computers, pretended they were experiments, and then tried to figure out how could we replicate what somebody in an experimental lab could do, and determined that there really is a strange attractor with the following properties in this data, which was typically at the time fluid data, though actually the very first test was made on chemical oscillations. But so we took a dynamical system here where we knew the x, y, and z coordinates, and we could simulate it. We said, let's assume all we can observe is the x coordinate. We can't observe y or z. Can we replicate something about it? Well, we discovered if we just took derivatives, which we could do easily with our analog computer, we get something that looked like this. Looks different, but actually we could show that it had the same Lyapunov exponents, the same fractal dimension, all the same geometric properties as the original thing. And so in fact, that allowed people to then go and say, yes, we saw a strange attractor in this chemical oscillation with the following properties, and then fluid flows. And it allowed me at the time actually to come up, John Sidorowicz and I, to come up with forecasting methods that took advantage of situations where you had deterministic chaos to produce better forecasts than you could do with a conventional time series model. This is the formula that we derived for the accuracy of our forecasts as a function of parameters like the number of data points, the leading Lyapunov exponent of the dynamics, which were things, that's something you often could infer from the data. And so, and we applied this to fluid flows and showed that we could beat standard linear time series forecasting models by orders of magnitude. Now, let me just say that there's a key challenge to understand how to use the data assimilation methods that have developed a lot since what we did back in 1980 so that they can be used in agent-based models. And I'll come back maybe and say a bit about this in a moment, and I'm about to try and wrap up. Let me also say we've been working hard to try and put together a software library for doing economic simulation. Each domain of simulation has its own unique problems. In economics, you typically find that you need to have agents with balance sheets, so you need to be able to do accounting. They make contracts with each other. You need to make that easy to do. They interact with markets. You need to make markets simple to simulate. They form expectations. So we're trying to build up a library of tools for doing that kind of things in an open source project. These are some of the applications my group's working on: housing markets, financial stability and systemic risk, simulating the insurance business with a grant we have from the Amlin company, trying to understand when boundedly rational agents will actually converge to equilibrium in a more theoretical way, and understanding technological progress, growth, and the green energy transition. And we have a goal, and the last one I should have put a question mark because we aren't really doing that now, of modeling international economies. And we have in the past made a model that has all the basic elements. We want to do things like this, but do them better than we did in this rather hypothetical model. Now, my vision for economic simulation is that we make a real-time tandem simulation of the economies of the major countries of the world. We use micro big data inputs directly off the internet, and this is where data assimilation comes in, because we aren't going to just get GDP and so on. We aren't going to know exactly what the coordinates of each household in the world, or even in the UK, or even a Monte Carlo sample of them are, unless we get people to participate, to give their data to us. Who knows? Maybe some people will do that. We will be taking other stuff off the internet, like how many diamond rings are selling on Amazon, or stuff like that, that gives you some indicators about what the economy is doing. It turns out, for example, that if you just look at traffic, how many cars are crossing a marker on a road in Holland? The Dutch did this and tracked it for 10 years. It correlates very precisely with GDP. More traffic when GDP's up. So we're going to have data inputs like that, and we're going to have to figure out how to get them into the model and make successful analyses with them. I imagine teams focused on each of the basic parts. There's a household team that's really trying to monitor what households are doing. Think about the household simulation model. Are we simulating the diversity of different households? Because of course it's going to be a very heterogeneous set of agents in the right way. Now, I want to conclude by saying that in my experience, I'm an old guy with a beard, a long gray beard now. But I've lived through several revolutions and successful revolutions in science at this point. When a new field opens up, there's this flurry of activity where you make significant new innovations because you open up major new questions and there's low-hanging fruit. So you don't have to be super smart. You can just go out and solve some problems that can turn out to be path-breaking. I offered that example of our technique for finding strange attractors in data. That turned out to be super useful. The paper has 4,500 citations. It would have even more, except that Tockins came along a year later, and Flores Tockins came along a year later, actually proved a nice theorem about how to do it. And so a lot of people reference him now, which is fair. But the point being that when you start something, you really can make a big difference. There's a kind of S-curve, I would argue, in innovation. You start out doing the really fundamental stuff, then at least along the line that you're working in, you at a certain point tend to saturate, and new fundamental innovations aren't coming along anymore. That doesn't necessarily stop the flow of papers. Papers keep getting published. Oftentimes applications drive that. And that's still interesting and important stuff to do. But if you want to make really fundamental innovations, which I think the Alan Turing Institute wants to do in data science, you need to find the fields that haven't done what they really can do, get in early, and make foundational papers. So I've seen this happen in chaos, where when I first learned about it and when I was in graduate school, it was a completely weird thing that nobody had ever heard of. And we sort of boldly set out and wrote papers in it despite having no advisors and it not even being a recognized field. Well, that turned out to be a really good thing to do. Of course, we could have picked something that wasn't successful and it would have been a dud. Machine learning is another example. The people like Jeff Hinton that made foundational approaches to building neural nets, that's reaping huge benefits now, but 30 years later. But I would argue that, the progress in the last 10 years has not been it hasn't made fundamental alterations in what the models are. Such kind of progress may still be possible, but I suspect it will involve opening up whole new lines of inquiry. Complex systems, I put a question mark. That's another field I've been involved in. Complex systems is a bit different because it's a sort of giant category of problems to be solved rather than a specific set of techniques for solving them. Things like network theory has been hugely successful, but network theory is only solving a piece of the complex systems problems, and there's still foundational stuff to be done. Those problems are really hard. I think they're going to take 100 years to resolve. But my conjecture is that simulation is a problem that's still in this early stage. I hope I've convinced you that there's really basic things that need to be done if we want to make quantitative simulation models that can allow us to do policy analysis and compete with the best models that are out there already. And so that was the main message of my talk, and I'd like to end there.